All right, let's do this. So we want to talk about WebSocket frames today. Let's do exactly that. All right. So on Monday, we introduced what WebSockets are, and we went through the WebSocket handshake. So we have this setup to the protocol where we get an HTTP request, and we send a very specific HTTP response. We compute that accept, we send the response, and then we keep that connection open, enter an infinite loop, and keep that connection open, and then speak WebSockets over that connection. We've upgraded the TCP connection to a WebSocket connection by doing that. And then we're going to call our receive method and our send all method to be able to receive and send WebSocket frames over that connection. So that's what we want to talk about today, is how we're going to send messages over the socket, what the format of those messages are, how to parse them, and how to construct them to send them. That's our big thing today, because we already have the connection. We're in a loop. That top of that loop we're going to call receive. Those bytes are going to be the bytes of a WebSocket frame, not an HTTP request anymore. And we need to make some sense out of those bytes, parse them, get the information out of them, and then broadcast that information, because for our homework, for our application, it's going to be a chat app where we broadcast that to all users. So once we get the message, sending that message out to all WebSocket connections using send all, then going back to the top of our loop and doing it again until the client closes that connection. So this is the format. We're going to stare at this most of today and make sense of every piece of information on this protocol, on this diagram. We're going to make sense of all of it. But before we do that, let's back up a little bit and talk about protocols. We use protocols all the time. You've been using protocols since 1.15. We use them all the time in different contexts, and sometimes it means slightly different things. But it's always going to mean an agreed-upon set of rules. Protocols are what kind of makes the magic happen. We have the HTTP protocol we've been studying all semester. We have it defines things like /r/n is our new line character, and we're going to have headers that are ASCII only. We have request lines, and we have status codes, response codes, and all this stuff. And if we study that RFC, we study how HTTP works, and write our server code to speak that protocol. And the people developing the browsers, writing code to build browsers, they follow the same protocol. They read the same RFC and follow the same specs. We both implement the protocol, then we can make sense of the bytes that we send back and forth. Because over the internet, we can only send ones and zeros. We have to make sense of those ones and zeros somehow. With HTTP, we say everything before the 4 bytes of /r/n/r/n, everything before that's all ASCII only, so we can use a text encoding to make sense of those bytes, and we have specific ways to represent headers and requests and all that. And we've seen this with TCP and IP. We didn't talk about it in detail about these protocols. But if you take modern networking concepts, I'll always pitch that course. If you take modern networking concepts, you can figure out everything that happens in these protocols and much, much more. So with these protocols, these ones specifically are going to represent information based on the position of each bit. So as opposed to HTTP, where we say, okay, parse this using text, and then we do all our text parsing, how we've started the semester. With these protocols, TCP and IP, we're looking at the positions of the bits. So if we get an IP packet, if I'm a router on the internet and I get an IP packet, it's not really an IP packet, it's just a sequence of ones and zeros. That's all I'm getting. It's all I can get. High and low voltage, light and no light, that's all I get. What I'm going to do is look at the first 4 bits that I receive, and those first 4 bits, I know that whoever sent me this packet is following the same protocol. The first 4 bits are going to be the IP version of this packet. So the IP version in 4 bits, which is for our purposes, for the modern internet, is going to be either 4 or 6. So I'm going to see 0, 1, 0, 0, or 0110. We're going to see one of those two values as the first 4 bits to specify what the HTTP version is. And then based on the version, I'm going to parse it accordingly. This is an IPv4 header. So if it's IPv4 for the version, I'm going to read the rest of these pieces of information based on their position. The next 4 bits are the IHL. The next byte is the type of service. The next 2 bytes is the total length, etc. That's how I'm going to parse all of this information based on the position of the bits. And that's what the protocol tells us. And that way we can make sense of the ones and zeros without even using a text encoding. Same thing with TCP. TCP, the first 2 bytes are going to be the source port. Second 2 bytes are the destination port. Next 4 bytes is the sequence number. Next 4 bytes is an ACK, etc. So based on where the ones and zeros are, I can get just a whole bunch of ones and zeros and say, okay, this one's in this position. That means it's this bit of this value. We're going to do that same thing for WebSockets. So as opposed to HTTP, WebSockets is going to use the position of individual bits to assign information to them. So for example, the first bit is the FIN bit. The next 3 bits are the reserve bits. The next 4 bits is the opcode, mask bit, payload link. We're going to go through all of those in today's lecture so we know what every single bit means when we receive a WebSocket frame. And to put it all together, if we have an IP packet going through the internet that uses TCP for transport and is transporting a WebSocket frame, when it's going through the internet, that packet's going to look like this. The first bytes are going to be the IP headers. The next bytes will be the TCP headers. The next bytes will be the WebSocket headers. And then finally, the actual payload of the WebSocket, this information of what we're actually communicating. And when this packet's going through the internet, the routers of the internet are going to read the IP headers, and everything below it is just the payload. It doesn't care what the bytes are. It doesn't even care that it's using TCP or WebSockets. It's going to read the IP headers, figure out where to send this packet using the destination address, and send it on its way. By the time this packet gets to its destination, the host device, that device, is going to remove the IP headers. The IP headers already did their job. Once a packet gets to its destination device, IP headers did their job. We tear those up and throw them out. We're done with them. Then the host machine is going to look at the TCP headers. The operating system is going to look at all of these and figure out where this packet should go. Most importantly, the destination port. It's going to look for which process on the device is currently using that TCP port, and then send this message. It's going to do the sequence number thing if it has to. If it's a large message, it'll piece it all together. And once it has the final message, it's going to go to the process that's using that destination port and say, here's your message. And at that point, we're done with the TCP headers. TCP did its job. All of its sequence numbers and the three-way handshake, all that stuff's done. I mean, you could try a little harder. It's every day. So then we throw away the TCP headers and get this message to our program, the process that's using that destination port, which is going to bring us to the application layer. HTTP, WebSockets, these are application layer protocols. So we get to the application layer, and this is what our application actually cares about, is the WebSocket headers. You know, it's bugging me now that I didn't line these up. Why do I have these all off kilter? I didn't even notice that in the first lecture. So we finally get the WebSocket messages. So once we get the message, the IP headers, the TCP headers, they're gone already, and the first byte that we read when we call receive in our code is going to be this first byte. Same is true for HTTP. The HTTP will be the payload of the packet, and the first byte will be either a capital G, a capital P, depending on what the HTTP method is, what the first character is. So since we're about to talk about WebSockets and it follows a protocol like this, I think it's a good place to remind y'all what IP and TCP are. That's as deep as I'll go into IP and TCP. But again, modern networking concepts will go way deeper into the other layers of the network stack. We're mostly concerned with the application layer. in this course? Because we're building apps. I mean, it's web applications. Makes sense, right? Okay, so how do we make sense of this? Let's parse this, piece this apart. This diagram is right from the RFC. So I'll give my bullet point explanation of each thing. If you want more detail or you just don't like the way I explain things, the RFC is always there. It's linked from the course website. It'll have the same exact diagram, and it'll have its explanation with all the detail, every single detail about WebSockets. It'll have that full explanation. So if you do want more explanation, this is right from the official documentation. And to do this, we're going to have to parse at the bit level. This is what I always get excited about for WebSockets, because we learn about bits from day one of computers. I guess not day one, but when you first start 191, we learn about bits, but we don't usually have practical applications for bits. When we're parsing these WebSocket frames, we actually have to care about the individual bits of this message. So let's do a quick refresher on how to handle our bits. And then I'll kind of leave it to you. I'll assume you're well refreshed, and then I won't talk about it again after this slide. But it should be flashbacks to other courses, the 191, 220. If you took 341 by now, this should all seem quite familiar. But just a quick reminder, bitwise AND is going to be a useful operation for us here. And we want to remember that bytes are 8-bit integers, unsigned, and when we read from our TCP socket, we're going to get this information as an array of bytes. Oh, let's see if it happens again. It wasn't bad. Sometimes it doesn't, sometimes it doesn't. It's weird. But we have an 8-bit integer as our value, and that 8-bit integer is 8 bits. It's 8 ones and zeros. And we have multiple pieces of information in a single byte. So for example, if we want to get the opcode, we're going to call our receive method. That gives us an array of bytes, and we can index it. There hasn't really been a use for this so far in the semester, but now we will have use for it. It's an array, and we can get bytes by index. So if we call receive, we get our received bytes, and we say receive bytes of 0 using array syntax, that'll return just the first byte. So if I want to read the opcode, I'm going to get the byte at index 0 after calling receive, and this would be, to get the big picture, this will be inside your infinite loop after you already did the WebSocket handshake and did all that stuff. Inside that loop, you call receive, and the first byte that you see is going to be the fin bit, the 3 reserve bits, and the 4-bit opcode. So we have all these values in one byte, and we want to isolate each individual value. So if we want to isolate the opcode, that's the 4 least significant bits. What I want to do is bit mask it, and that's going to be a bitwise AND with a value that has ones in exactly the positions I'm concerned with. So if I want to mask out the opcode, I'm going to mask that with 15. 15 is 0000 1111. So if I do a bitwise AND with the first byte in 15, it's going to zero out my 4 most significant bits. So whatever they were, I don't care about them. I'm going to throw those away for now. And it's going to isolate my opcode, my 4-bit opcode, and give me that as an int. So for example, if I take the first byte and AND it with 15, and I get 8, then I know the opcode is 1000. If I get 1, I know the opcode is 0001. So that's going to tell me, based on whatever int is returned, what my opcode is. And then I can do the same thing for the fin bit. If I want to get the fin bit, I'm going to AND with 128. That's going to isolate that most significant bit. And if the result is 128, I know the fin bit's 1. If the result is 0, I know the fin bit was 0. And we use ampersands for this. Ampersand in most languages is the bitwise AND operation. If you ampersand 2 ints together, it's going to do a bitwise AND on the actual bit values of those ints. And if you're ever wondering, this is why we use ampersand for a logical AND. You might think when you're first learning programming, like, why don't we use just one ampersand? Well, it's because that's reserved for bitwise operations. Bitwise operations came long before logical operations. Bitwise operations are part of the CPU's instruction set. They've been around forever. So when they were assigning symbols to operations, ampersand was assigned to the first operation, the lower level operation. We just kind of, these days, everything's higher level. We got away from the bit level operations. We end up using logical and more than bitwise and these days, but that's why you have two ampersands. Same with OR. A single pipe is a bitwise OR. A single caret is a bitwise exclusive OR, which we'll actually see later today. So, long story short, we use binary. It's all binary. Get used to binary when you're extracting all this information. Okay, now since we had that refresher, hopefully that was just review. I know conceptually you know all that stuff, but you might not have wrote code that does that stuff. You might not have written Python specifically as well. But the concepts there better have been review. If that wasn't review, oh man, I worry. Okay. So now let's go through, now that we had that quick refresher, let's go through all the bits of this thing and make some sense out of all the bits. So if there are questions about binary or anything else as we're going, make sure you do ask, because I would really be worried, because I don't want you going through the rest of this lecture if you're already confused. And I'll keep my eye on chat as usual. Okay, so the first bit, the very first 1 or 0 that we receive for a WebSocket frame is going to be the fin bit. This is going to be a 1 if this frame is the last frame of a message, and 0 if it's not. So the WebSockets do have this functionality to be able to send a single message across multiple frames. This is a topic I'll get into more in depth on Friday. I'll leave it at surface level today. But if we get a frame and the fin bit is 1, then we know that that frame is the only frame for the message. We can parse the message, figure out, extract the payload, and that's the message. If it's 0, then we have to keep parsing web frames. We'll parse the web frame, read another frame, and keep reading frames until we read one that's a fin bit of 1. And once we get to that one that's a fin bit of 1, take the payload of all of those frames, concatenate them together, and that's my overall message. So if we see a 0, we know that we have continuation frames coming, and we have to concatenate all of the payloads of all of those frames to get one single message. Next are the reserve bits. So the next 3 bits are the reserve bits. These are the easiest ones because we're just going to assume they're all 0. You don't even have to check what they are. I won't get mad at you if you completely ignore the reserve bits. As the name implies, they're reserved for future functionality and extensions that you can add on to WebSockets. We're not going to mess with any of that, so we're just going to say they're all 0. The browser, I have never seen a browser ever send a reserve bit that was not 0. You would have to do something on your front end to explicitly say we're using these reserve bits. You're never going to see reserve bits that aren't 0 in this course. Opcode is a 4-bit value telling you the type of the payload. Most of our messages are going to be 0001 or just 1 for text to say that the payload is text. You can also specify binary. If your opcode is 2, then your content, your payload is binary. So we're not going to, but we could use WebSockets to send our images and videos, any binary data that we have. We could use WebSockets for that. We would change the opcode to 2, and then the browser's going to know to not use any text encodings for the content of that WebSocket frame. We're not going to. I already hit you with images and videos using multi-part forms in Homework 3. I don't feel the need to hit you with it again. I want Homework 4 to be focused on the WebSockets themselves, so we're not getting bogged down with too many extra features that are not really related to WebSockets. So we're always going to be sending text. Next is 8. If I get an opcode of 8, that's going to be a close operation. This one we do have to worry about. If you get a close, that means the client is closing the connection. This is going to happen when the user closes their tab or their window. The browser is going to clean up that WebSocket connection by sending us an opcode of 8. And whenever we see that opcode of 8, we need to sever that connection. We need to get rid of that connection. This is going to be important. When we see this opcode, that's the only time we're going to exit our infinite loop. Well, I guess other than shutting down the server itself. That's when we're going to exit that infinite loop. So we do have a while true. It's going to seem infinite, but we're going to have an if opcode equals 8, break. Break out of the loop, end the handle method. That closes the TCP connection. Clean up any data structures you might have. You should have a data structure. And I went off on a little tangent in the other section, so I'll do it here. Actually, let me talk about continuation frame first, so I got all this. 0 is continuation frame, so if you have a frame with a fin bit of 0, the next frame will have an opcode of 0 because it's a continuation frame. And you'll see frames of 0 until one of them has a fin bit of 1, then the next frame might have a different opcode. That one, if you assume that it's 0, if you see a fin bit of 0, you can assume the next frame is going to be an opcode of 0. I wouldn't be mad if you didn't check. If you don't, nowhere in your code you have if opcode equals 0, then it's a continuation frame, I wouldn't be mad at you. The close we do have to check for. So the way we'll set this up, and I might be able to do an example. This one's hard to describe without the code, so I might try to squeeze in an example on Friday. If I don't, it'll be a recitation example, which recitation is where they do all the demos and examples. Lecture focuses closer on the content, the concepts, and everything. Recitation is where the demos are. So those of you who aren't going to the recitations, that's where they bridge the gap between what I do in lecture and how to get started on the homework. So if you're feeling like that's missing, maybe go to recitation. Just a suggestion. But anyway, so I'll give a quick description of how this works right now. So when you have a WebSocket connection, there's a few things we need to do. You get a WebSocket connection. During that WebSocket handshake, that's your only chance to authenticate the user. That's when you're going to see the cookie with their auth token. That's when you're going to authenticate the user. You're going to use your homework 2 code for that. Homework 2 code should handle that. Hopefully you just have a method call to be able to handle that, to get the user, do all the database stuff and hashing and all that good stuff. They should just be in a helper method. So call your homework 2 code, get the username, and store that in a variable, and then enter your infinite loop where you're going to handle your WebSocket frames. The first line of that, well, maybe not the first line, but at the top of that for loop, you're going to call the receive method. And we're going to need to call the receive method. We're going to have a reference to the handler for that. And then when we parse the frames, we're going to need a reference to everybody's handler so we can call send all and broadcast this to all users. So there's two problems that we need to handle here. And both of them involve having references to the handler method. So when you have the handshake, you have this WebSocket handshake, and you agree that this is a WebSocket connection. When you create that connection, you have a reference to that connection through self if you're in the handle method. And it's easy to not think too much about it, but now we have to start thinking about it. When we do self.request.sendAll, self is a reference to a myTCP handler object. If you didn't rename the class, it's whatever you name the class. It's myTCP handler in the handout code, though. You have a reference to an object of that type, which has the request field, which has the sendAll method, which you're using to send data over that WebSocket stream. Now, if you're in the handle method, that's pretty straightforward. You do self.request.sendAll, and you don't think about it too much. But now we're going to be in different parts of the code, on separate threads even, in different infinite loops. And in each one of those loops, they need to be able to access all of the handlers for all of the open connections. So we're going to need a data structure to store those things. What I recommend you do is create a hash, I'm thinking 116, a dictionary of username to handler object. You do your auth stuff, call your method from homework 2, get the username, add that as the key to the dictionary, and the value is, if you're in the handle method, self. If you're using the router, I recommend adding a handler parameter to the route request method, and I give that hint in the homework. If that doesn't make sense right now, it's in the homework handout as well. Add a second argument so you have access to that handler object inside the function that you routed to that's going to have your infinite loop in it. So you have a reference to that, so then you can call send all on it and receive on it. And then that data structure needs to be shared across all threads. So if you're using the router, or if you follow the router example in lecture or in recitation, wherever you're putting the router, if it's a package level variable or a class variable in the TCP handler class, wherever it is, put it somewhere where every file can access it. So across different files, you can still grab that data structure. Even across threads, you can grab that data structure and share data across those threads. Now when you parse a frame, you have the chat message that somebody sent. You go to that dictionary, you iterate over the values, and call sendall, .request.sendall on all of those values. So hopefully that makes at least a little bit of sense. I know I'm trying to describe code just by waving my arms around. It doesn't always work that way, but that's my hint. That's kind of my rundown of the architecture that I recommend you follow in Homework 4. Some of you will do it different ways. A lot of you will probably just stuff everything in the handle method, and then wherever you put your variable, it's shared. And I don't know. Some of y'all do different things, but whatever you do, you got to solve those problems, and that's the way I recommend. Especially if you're using the router, add that extra parameter, and then you have access to your handler method, handler object, so you can call receive and send all. And then have the shared data structure, so you can call send all to broadcast messages over all WebSocket connections. Okay. That was planned. That wasn't a tangent. But let's keep moving. Okay, next is and I like having that tangent there because we're about to get into payload length, which is the most complex part of WebSocket frames. So I want to make sure you understand that first byte. We only got through the first byte of these messages so far. So hopefully that had time to digest while I was talking about the other stuff. Anyway, next is the mask bit. This is either 1 if a mask is being used or a 0 if it's not. And if this is 1, then there will be a 4-byte masking key here. If it's 0, this key doesn't exist. This will always be 1 when you're receiving a frame, and it will always be 0 when you're sending a frame. So whenever you're creating frames, this is always 0, and this doesn't exist. When you're receiving frames, this will always be 1, and this will exist. So you don't have to have any conditionals. I wouldn't be mad if you'd never checked the mask bit either. It will always, always, always be 1 when a browser is sending you a frame. But you do have to check the masking key. Masking key, when we get past payload length, I'll talk more about what that actually does and what that means. For now, I just want to mention the mask bit itself. Okay, and then payload length. This is the bulk of it here. This is the bulk of your frame parsing and creating frames. I'd say this is the bulk of LO1, and I'd even argue that LO1 is at least half of the assignment, probably more than half. There's some tricky things with buffering, but I don't think they're nearly as much work as this. They're a little tougher to debug because it's harder to write test cases for the buffering stuff. These are easier to write test cases for, but this is, I'd say, the bulk of the work for the entire assignment is figuring out this payload length. So let's talk about it. Payload length, the next 7 bits. It shares a byte with the masking bit. The payload length has 3 different modes depending on the actual length of the payload. So the payload data down here, this is the stuff that we're actually interested in. This is what the user is sending to us from the front end, and it's what we're sending to the user from our server. The payload length is, I skipped this explanation. The payload length is similar to the content length. It's solving the same problem as content length. Content length told us, or more accurately, told the browser, we needed it for buffering in Homework 3, but the browser definitely checks payload length. But it tells the browser how many bytes to read. And it has to tell the browser exactly. You know by now that if you're off by 1 on your payload length, things don't work. If you have too small content length. If you have too small a content length, you don't get all the content. And if you have too large, there's endless buffering on the client side. The same thing is going to happen with payload length. We need to read the payload length to figure out how many bytes we have to read, and we have to read exactly that many bytes. And we're going to get a few extra features here where with HTTP, we always get a request, send a response, sever the connection. With WebSocket frames, our whole point, part of our point, is to keep the connection open, which means multiple frames are coming over the same connection. And if the client is getting aggressive and sending a lot of messages back to back, when we read bytes from the TCP socket, we might read more than payload length number of bytes of the payload, because we might start reading the next frame when we call receive. So we need to check the payload length to make sure we didn't overshoot how much we read. And if we did, we have to set those extra bytes aside, because those are the headers for the next payload, the next WebSocket frame. And we have to still make sure that we didn't undershoot and enter a buffering state if that's what's needed. So the buffering we're doing in homework 3, and making sure we don't overshoot. Overshooting is the new thing, and I'll have a deeper conversation about that on Friday of what to do when we overshoot. I did just say everything that I need to say about it, but I want to give examples of that because it causes a bit of confusion every semester. So we need to read the payload length, get the exact number of bytes, and make sure we grab exactly that many bytes. And there's 3 modes to payload length. If the payload length is less than 126 bytes, the payload length is this 7-bit value. So you're going to read these 7 bits. If this value is less than 126, that's your payload length. Easy day, done. Make sure you mask out the masking bit. Mask this with 2, oh my goodness, 1 something, 127. Oh, wait, that's obvious. Mask this with 127 and get the value. It's 1 more than, that's why this is 126. Anyway, and then get the payload length. That's the payload length if this value is less than 126, which means the next byte is going to be the masking key. All this extra stuff right here that the protocol says, none of that's there. And the next byte right here is going to be the masking key for 4 bytes, and then the payload length. And this is where the elegance of WebSockets really comes into play, really shines for me, is WebSockets is basically just using TCP with a little bit of overhead. We have, if our payload is less than 126, if we have a small message here, our overhead is 1 byte for the fin and opcode, 1 byte for the masking bit and the payload length, 4 bytes for the masking key, and then we're already into payload data. 6 bytes of overhead per message. That's it. That's almost nothing. Like, that's nothing at all. Compare that to HTTP. With 6 bytes of HTTP, we can't even specify the HTTP version number. It's HTTP/1, and then we have an extra 0.1. We have 8 bytes, and then we have /r/n. We have the 4 bytes for the blank line. Any headers, we might have hundreds of bytes of headers. We have the method, the path, those 2 spaces. We have a lot of overhead, comparably anyway, with HTTP. With WebSockets, it's made to be lean, it's efficient. It is a very elegant, clean protocol. It basically just uses TCP. The TCP and IP headers we saw before, there's way more overhead just in those headers. And WebSockets really doesn't add much at all to it. Not much overhead at all. 6 bytes of overhead. Almost nothing. So you're just using raw TCP with a tiny amount of overhead. Okay. If the payload length is larger, we do have a little more overhead. We're going to have 2 extra bytes of overhead in this case. If we have greater than or equal to 126 but less than 65,536 bytes, strictly less than, then we're in the second mode of payload length. If this is the case, the payload length, the 7-bit payload length right here, is going to be exactly 126, which is 6 ones and a 0. So it's going to be exactly the second highest value that we can represent in 7 bits. And if we see this 126, that tells us that the next 2 bytes is our actual payload length. So if this is 126, it says read the next 2 bytes, smash those 2 bytes together, read them as one integer value, and that's your payload length. And since we're using 2 bytes, we have 16 bits. 2 to the 16 is 65,536. So we can't represent that value. We can represent one less than that. That's why it's strictly less than. And the endpoints are important. I am testing the endpoints in Autolab. We have to get these numbers exact. So less than 2 to the 16, we can represent with our 16-bit payload length. And it can be exactly 126. If it's exactly 126, this value is 126. And this value will also be 126. And our most significant 8 bits will be all zeros. It'll just be zeroed out. So if the payload length is within this range, 7-bit payload length is 126, and then the next 2 bytes is our payload length. If our 7-bit payload length is exactly 127, all ones, then the next 8 bytes is going to be our payload length. So the next 8 bytes, 1, 2, 3, 4, 5, 6, 7, 8, using all of this space is going to be our payload length, and then the next byte will be our masking key where it is visually on the diagram. That's where the masking key will actually be. If this is our payload length, we have 127, and we use the next 8 bytes, we can have payload lengths up to 2 to the 64, which is this number, or 16 exabytes, 16 million terabytes for our WebSocket frame. They really wanted to future-proof this protocol. Not only can we have 16 exabytes of payload, we also have this fin bit and continuation frame mechanism to be able to have multiple frames, just in case this wasn't enough, which I'm being a little bit, silly there, but because there are good reasons to split up, even if you have less than 16 exabytes that you're sending. You usually do want to split things up into multiple frames. This is a feature we have to build. Chrome, specifically, any Chromium-based browser, once you send a message that's more than 131,000, seems to be the magic number, bytes, it's going to split that into multiple frames, that one message into multiple frames. So to test that feature, we go higher than 131,000, much shy of 16 exabytes, and send a message with that. Make sure Chrome split it up into 2 messages. And I have seen, much to my frustration, I have seen Chrome with significantly smaller messages still splitting it into two frames, one message into 2 frames, which is frustrating because I've tried last semester to not require the continuation frame and FinBit stuff on the homework, and a lot of students ran into it anyway. It caused a lot of confusion, a lot of bugs, a lot of issues. Surprisingly, it's just easier to require it, so you know what to expect, you know what you're seeing when you see it, and you're expecting it, you're writing code to handle it, and it's less headaches that way for all of us. Surprisingly, I actually did try. I didn't actually want that feature to be on there, but it's a weird situation. So to read the payload length, you read the 7-bit payload length. If that value is exactly 126, read the next 2 bytes as your payload length. If it's exactly 127, read the next 8 bytes as your payload length. Otherwise, this itself is your payload length. And however many bytes you had to read for the payload length, the next 4 bytes are going to be your mask. And you have to do the same thing in reverse when you're creating your frames. You're going to check which range you're in, what size message you have, how big your payload is, figure out which of the 3 modes you should be in, and then create your payload length based on that. Either set this to 126 or 127, use the next 2 or 8 bytes, or the 7-bit payload length is just your payload length. Okay, any questions on payload length? Am I on mobile data? What the hell? Won't connect automatically. Why don't you connect automatically? I hate that I have to check that every time. So that's payload length. Again, I'll always qualify this in my opinion, because there's still nobody calls me out. But handling payload length on both parsing frames and sending frames is, in my opinion, the bulk of the work for this. It's at least 51% of the work. There's still some work to do after that, especially with buffering, multiple frames back to back, and fin bits of 0 and continuation frames. All that will be some work as well. but the payload length, the homework is pretty front-loaded with that one. Okay, no questions on payload length. Let's do it. Let's keep moving. Okay, so we talked about mask bit. It's either 1 or 0. If it's 1, the next 4 bytes after the payload length, no matter how many bytes the payload length took up, the next 4 bytes are going to be the masking key if the mask bit is 1. Every single frame you receive from the browser, every single frame you ever parse, including in my test cases for LO1, I always set the mask bit to 1 when you're parsing frames, and it's always going to be 0 when you're generating frames. So I don't have any test cases where the mask bit's going to be, oh, surprise, it's 0. It's always going to be 1 when you're parsing frames, every single time. So when you're parsing frames, these next 4 bytes after the payload length are always going to be your masking key. When you're sending frames, when you're creating frames, you're always going to set the masking bit to 0, and these 4 bytes will not exist. Right after whatever you have for payload length, the next bytes when you're creating frames to send, you're going to go right into the payload data, which is unmasked when you're sending them. Okay, so when we're receiving a frame, this will be 1. And the way this works is the masking key will be a completely random value. It will be different for every single frame ever, though, well, with probability 1 over 2 to the 32. Will be a different value every single time. And it's going to mask the payload byte for byte. So the payload data is going to be masked with this key using an XOR operation. So each 4 bytes of payload data are masked with the 4 bytes of the masking key. For example, I got to spell this one out. Bear with me. The first byte of payload data is going to be XORed with the first byte of the masking key. The second byte of payload data will be masked with the second byte of the payload key, or the masking key. Third byte of payload data is masked with the third byte of the masking key. Fourth byte of payload data is masked with the fourth byte of the masking key. And the 5th byte of payload data is masked with the first byte of the masking key, and then that pattern follows until you're out of payload data. The reason I want to spell it out is you might be tempted to take 4 bytes, every 4 bytes of the payload data, and mask it with the masking key. Don't do that. Please don't do that. If you're grabbing 4 bytes at a time and XORing with the whole masking key, you have a 75% chance of getting an index out of bounds error when your payload length isn't divisible by 4. So don't get into that trap. I would do this 1 byte at a time. Iterate over the indices of your payload data. Get the indice, the byte at index 0, mask it with the masking key byte 0, and for each index, get the byte of payload data, take the index modulo 4, and get the index of the masking key based on that value, and then XOR them. So you can do this cleanly in a loop where you're looping over every byte of the payload data and handling them 1 byte at a time instead of trying to do it in chunks of 4. Don't do it in chunks of 4. If I see index out of bounds error, that's the first thing I'm going to look at in office hours. I'm going to see if you're chunking this in chunks of 4, XORing it. The reason for this, which I don't think I have in a slide anywhere today, I think it was in Monday and I deleted that slide. But the reason for this whole mask and payload business, it seems like nonsense. Just like any other nonsense we talked about in this class, it's to break caching. If anything's tempted to cache something, it's not going to anymore because every WebSocket frame looks completely different. Even if you're sending the exact message every single time, the masking key is going to be completely different. So it's going to look like different frames, different data, and nothing along the pipeline is ever going to say, hey, we should cache that thing, because it's going to be a different message. And then our responses, we don't mask our responses because the client's not going to cache messages that we send to them. That doesn't make sense. That's not what caching is or what it does. Caching is going to be when we're getting things from the client to save efficiency on our end. So we don't have the same problem, so we don't use masking when we're sending messages to the client. But the client sending messages to us, there is a risk of caching. In this case with WebSockets, we don't want any caching ever. So we have this masking mechanism to bust up the caching. Okay, so as an example, say these are the 4 bytes of my message, and the client generates a random mask of this. What they're going to send as the payload, the actual payload of the WebSocket frame we receive, is going to be the message XORed with the mask. So 0 XOR 0, 0, 1 XOR 1 is 0, 0 XOR 1 is 1, et cetera, et cetera. This is what's going to be the message. When we get that payload, we're going to XOR it with the key again. So 0 XOR 0 is 0, 1 XOR 0 is 1, 1 XOR 1 is 0, and we're going to get back to exactly the original message. And mathematically, if you think of the full operation we did was the original message XOR the mask equals, well, the mask XORed with itself is going to be straight zeros, and the message XORed with straight zeros is going to be the message. So XORing the mask twice, which effectively we do, is going to get us back to the original message. And XOR is a very fast operation. We like XOR. It's, I mentioned earlier, it's an operation in the instruction set of the processor itself, one clock cycle. We like XOR. Any bitwise operations we like. Okay, so you go through the whole payload one byte at a time, unmask it with the appropriate byte from the masking key. That's going to get you the message that was actually sent in plain text, and then you can start finally processing it. That'll be for our purposes, for the homework, a JSON string with a key that's an object with a key message, and the value is whatever the user typed in. Send that to your homework 1 code. Generate the ID for that message, store it in your database, all that stuff. You have the username in a variable that you did during the handshake that I mentioned forever ago, because you called your homework 2 code to get the username, slap that variable in as the username for this message, send it to your homework 1 code, stores in the database and everything. And then the new thing is we have to broadcast it to all of the WebSocket connections that are currently open. We talked about that earlier with the data structures and everything. That's kind of the rundown of everything that we do. Oh, yeah, it's the char. I forgot to mention the operation. I thought I had it in a slide, but I guess I did XOR in the slides. It is not a security thing. So the payload comes with the mask, so there's no security, because anybody who grabs the message has the key as well. It's only to bust caching. It's only to prevent caching. No security at all. We'll eventually get to encryption. In 2 weeks, we'll get to encryption. We'll talk about security. Okay. And then when we're creating frames, same exact format. So a little different from HTTP, where HTTP was slightly different. The first line of a request is different from the first line of a response. Not the case for WebSocket frames. Same exact protocol, same exact structure, except the masking key will be 0 when we send it. The masking key will be 1, or masking bit will be 1 when we receive. That's the only difference. We're never going to send a frame with a fin bit of 0. We're always going to send our messages in one shot. There's no need for us to do that. It'd be really cruel to add that to the homework.